All right, let's talk about a technology that honestly feels like it's been pulled straight out of a sci-fi movie, quantum computing. This stuff operates on the, well, truly mind-bending rules of quantum mechanics. And we're not just talking about making computers a little bit faster. No, this is a completely different way of processing information that could change pretty much everything.
So let's just start with a huge question. What if we could build a computer that could solve problems that right now we consider impossible? I'm talking about things like designing brand new medicines from scratch, creating perfect models of climate change, or making sense of the chaos in global financial markets. These are challenges that stump even our most powerful supercomputers today, and that is the incredible promise of quantum computing.
Okay, so let's get into it. To really understand where we're headed, we first have to get our heads around the massive, revolutionary leap from the classical computers we use every single day to these quantum powerhouses of the future.
So the key difference, the real heart of it all, comes down to one thing: the basic building block of information. Your phone, your laptop, everything runs on what we call bits. A bit is super simple, right? It's just a light switch. It's either on, which is a 1, or it's off, a 0. That's it. But a quantum computer, it uses a qubit. And the best way to think of a qubit is like a dimmer switch. It can be fully on, it can be fully off, or it can be a mix of both states, all at the exact same time. This one little difference is what unleashes this tidal wave of computing power.
Now that we've got the basics down, let's pop the hood and take a look inside. We're going to look at a couple of the really strange quantum phenomena that give these machines all their muscle. And trust me, this is where things start to get a little weird, but also really, really cool.
Okay, so let's just pause on this one idea for a second. The qubit. This ability to be both a 0 and a 1 at the same time. It's not just a cool party trick. It is the engine that drives everything else we're going to talk about. So what does that power actually look like in practice?
Well, here's where you can really see the mind-blowing difference. If you have 8 classical bits, you can represent just one single number between 0 and 255 at any given moment. But if you have just 8 qubits, you can represent all 256 of those values at the exact same time. It's not just about being faster, it's about a kind of parallel processing that just grows exponentially. The more qubits you add, this advantage just completely explodes.
Now, this dimmer switch behavior has a scientific name. It's called superposition. It's one of the absolute core principles of quantum mechanics, and it's what lets a single qubit explore tons of possibilities all at once, which is what gives a quantum computer its massive parallel processing ability.
Now, look, if you thought superposition was a little strange, entanglement is, well, it's downright mysterious. You can link 2 qubits together in this really special way. And once they're entangled, if you measure one of them, you instantly know the state of the other one, even if it's miles away. It's this spooky connection that allows qubits to work together in these incredibly complex and powerful ways, solving problems that are just impossible for normal bits, that have to work all by themselves.
Okay, so we have these incredibly powerful concepts, but what do you actually do with them? I mean, that's the real question, right? And that's where quantum algorithms come in. You can think of them as these highly specialized recipes designed to harness all this unique quantum power for very specific, totally game-changing tasks.
And there are 2 really famous algorithms that we absolutely have to talk about. First up, we have Shor's algorithm, which you can think of as the code breaker. And then there's Grover's algorithm, which we'll call the supersearcher. Each one of these targets a problem that classical computers are just terrible at, and both of them have massive, world-changing implications.
Let's start with the big one, the one that gets a lot of headlines. Shor's algorithm is a direct threat to the very encryption that keeps our entire digital lives safe. Your online banking, your private messages. A lot of that security relies on a math problem that is incredibly hard for normal computers to solve, factoring really, really large numbers. But for a quantum computer running Shor's algorithm, well, it's not hard at all.
This really lays out the threat perfectly. So step 1, right now, your data is protected. Step 2, a powerful quantum computer comes along and applies Shor's algorithm. It finds the prime factors that act like the key to unlock the whole thing, and boom, step 3, the vault is open. A problem that would literally take a classical computer billions of years to solve is done in maybe hours, maybe even minutes. That is the quantum threat in a nutshell. On the flip side, we have Grover's algorithm. This is our super searcher. So imagine you're trying to find one specific name in a giant, totally unsorted phone book with a billion entries. A classical computer would have to check, on average, about 500 million names to find it. Grover's algorithm could find that same name in around 32,000 checks. This kind of speedup is absolutely huge for things like big data analysis, optimization problems, and AI. So you're probably thinking, if this technology is so incredibly powerful, why isn't it everywhere already? And that's a great question. This is our reality check. Because building and running a stable quantum computer is, without a doubt, one of the hardest engineering challenges humanity has ever taken on.
So here they are, the three main villains of the quantum world. First, you've got decoherence. Basically, qubits are unbelievably fragile. The tiniest vibration or change in temperature can make them just lose their special quantum state and become totally useless. Then there's error correction. Because they're so delicate, quantum computations are just full of errors that you have to constantly find and fix. And finally, scalability. Just building a machine with enough stable qubits to do anything useful is a monumental task.
And to give you a sense of just how fragile these systems really are, take a look at this number. That is 20 thousandths of a degree above absolute zero. To put that in perspective, that is colder than deep space. That is the kind of extreme temperature some of these quantum computers have to be kept at just to try and minimize all that environmental noise and stop decoherence.
And that error correction problem we mentioned, it is a massive resource hog. To create just one single, perfect, stable, logical qubit that you can actually use for a calculation, you might need to use thousands or maybe even millions of these fragile physical qubits, all just working to check for and correct errors in that one qubit. I mean, that is a staggering overhead.
So, okay, despite all of those massive hurdles, the race is on. And the reason for that is simple. The potential breakthroughs are just too big, too important to ignore. So let's take a look at what that future could actually hold.
The payoff for all this work could be absolutely immense. In medicine, we could simulate molecules to design new drugs in record time. In finance, we could create optimization models for trading that are just impossible today. We could build far more accurate climate models to better understand our planet. And in cryptography, we can even use these same quantum principles to build fundamentally unhackable communication networks.
And hey, remember that scary code-breaking threat we talked about a minute ago? Well, the good news is the smartest people in the world are already working on the defense. It's called post-quantum cryptography. It's a whole new generation of encryption built on math that's hard for both classical and quantum computers to solve, designed to keep our data safe long into the future.
And so, we end right where we began, with a question. This technology isn't just a leap in computing power, it's a leap in our ability to simulate, understand, and maybe even shape the world around us. But with that kind of power comes immense responsibility. So as we stand right on the verge of this new revolution, the real question isn't just can we build it, but how will we choose to use it? And that's definitely something we're thinking about.